Okay, so let's go on. So our goal today is to conclude this basic discussion of this very important correspondence in theoretical physics, which is a correspondence between a gauge theory and a string theory. It's an example. I hope to have convinced you that we expect this to be a rather general phenomenon, but here is a very sharp and very concrete realization of this very general phenomenon, where we relate a very precise 4-dimensional quantum field theory to a very precise 10-dimensional string theory in a very precise background. Okay? We should still, of course, establish more the dictionary. We saw that in both theories, the relevant couplings that we have in the game, we can all think in terms of the string tension and, well, N or Young-Mills, I choose the other one, whatever, to this, which takes into account genus counting in superstring, and in Young-Mills we have the Tooth coupling and the number of colors. So these are the two relevant parameters, so that's already part of the dictionary. These parameters are present in both theories. And what are the arguments for this duality? Well, there are several hints that we had before. So first we knew that in the large N limit, when we start drawing these diagrams, they start looking like the surface of strings. The topology works out and so on. That's of course very schematic. We know that there should be some duality between the physics of gluons and the physics of gravitons, because there is this alternative point of view that you can often think of closed and open strings as interchangeable, so there better be some kind of duality between gluons and gravitons, or more strongly between the physics of open strings and the physics of closed strings. And the strongest argument of all came from this decoupling argument. Decoupling stems from the fact that supergravity decouples from the rest. And the idea here is you take a stack of brains and go far away. So you go far away, so the brains are on that blackboard, and I go far away. What do I see? I see n equals 4 on that blackboard, which is my experiment, and a bunch of gravitons close to me. Okay, so far away, I see the gravitons far away, and some low energy physics which describe the degrees of freedom on the brain, which is n equals 4 super Young-Mills. There is another point of view. I can also say, here I am, far from the brains. There are still gravitons around me. There's still free supergravity. But if you remember, from my point of view, anything looks very low energy, which is happening close to the brain because of this redshift effect. So anything, if I take here some huge, very energetic material and carry it there close to the brain, it looks like it's a low energy excitation. So anything close to the brain, any closed strings, I can even put a black hole close to the brains and so on, anything looks like low energy for me. So I get this duality between the closed string physics in this non-trivial background, which is ADS5, and n equals 4 super Young-Mills once I cross out the supergravity part. Once I say they decouple in both sides, and therefore this better agree. This is almost a derivation. For some people it's a derivation, but it's not really, strictly speaking, a derivation, because this picture, to deform the background, I need the coupling to be large to really back react on the background. And here, typically I would like the coupling to be small, but it is just a convenience of the description. Then the claim is that once you establish this duality, you can use either theory to compute anything. But if you use string theory to study the limit of small string tension, which means small coupling lambda, well, you will have to suffer a lot, because you will have to do a path integral over all possible strings. And instead, if you use n equals 4 super Young-Mills, you don't suffer almost anything, because you just do a simple Feynman diagram, because the coupling is very small. Another piece of evidence for this duality, or something that told us that perhaps we were on the right track, was the statement that we are relating a 4-dimensional quantum theory to a 5-dimensional theory of quantum gravity. But we said that that's perhaps not a surprise, but rather something remarkable, but something that we should have expected based on these arguments of holography and the statement that black hole physics tell us that information is sort of contained in the area and not in a volume. Okay, so I would like to make a few more comments today. But any question here? Yes.
If we in the low energy limit, will this superstring theory also be a supergravity essentially?
If you take the low energy limit now further, another low energy limit of this string theory here, yes, it will be supergravity in ADS5.
So, but the duality is not restricted to supergravity?
No, no, no. It's low energy for this guy. So we take low energy for this observer, which is far away. Right? But for him being far away, it means anything here. Now, on top of that, you can now that you have this full duality, you say, oh, but string theory also contains gravitons. So I can also now take the low energy limit here and get the physics of gravitons. But that's already a particular limit of this duality. It's a weaker statement. Yes?
So why is it n equals 4 super Young Mills that is dual to ADS5? So can it be other for BCFT, or it's just n equals 4 super Young Mills?
The reason why it was n equals 4 super Young Mills comes from superstring theory, because if you ask what's the effective theory on the brains, it is n equals 4 super Young Mills. It's not up to you to choose. You compute the effective action describing the massless open degrees of freedom on a brain, right?
Okay.
And the answer is it's n equals 4 super Young Mills.
It's just, so you just calculate this green one.
You just compute, yeah. You just compute Born-Feld, compute effective action. It's a little bit like saying, I put, why do we get ADS5 and don't we get another background? It was not up to us. We just said, I'll put my brains as source in my Einstein equations and I see what I get. I cannot just choose. Same thing. It's a rigid construction in string theory. Okay? Okay. So, I would like to make a few comments now. The first comment is, or more comments. The first comment is that n equals 4 super Young Mills. Maybe. Okay. Okay, that's fine. So n equals 4 super Young Mills is a conformal field theory. Okay, so it's a theory without any scale. Okay, so a theory which doesn't have any scale. So did you know what a conformal field theory is? Theories without scales, massless particles, correlation functions of power law, and so on. Is it familiar? You saw it in some lectures, I bet, right? At least the words and so on. Yes? Very good. So, and therefore, in this theory, x mu goes to lambda x mu, so dilatations, is a symmetry of the theory. Okay? So, correlation functions transform invariantly, or rather covariantly, under this transformation. Now, suppose we want to try to understand what could be the background dual to a theory which is a conformal field theory. So if we write the metric in flat space, if we write just dx mu, dx mu, this is not invariant under conformal transformations. So there is a simple way of making it invariant, the simplest possible way. The simplest modification to make it invariant under dilatations would be to say, well, let me write this dx squared as dx dx, and I will divide by a new coordinate z squared, and say that z also rescales. When I rescale x, z also rescales. Now it's invariant. And I add some extra direction plus dz squared. Okay? So this will be the simplest metric that now has isometries that are related to dilatations of the x mu. Right? So this is the simplest metric you could imagine. And I just remind you that indeed this is ADS, or ADS 5 if here this is R4. Right? If this is Minkowski, then this is nothing but ADS 5. Okay? So ADS 5, if you want, is the simplest space-time that will have isometries that once you restrict these isometries to the background, they look like conformal transformations at the background. Yes?
Couldn't we just divide dx mu by x dot x and get something invariant under these scalings?
You could. That would solve the rescalings. But there is more. In fact, the isometries of ADS, not just dilatation, but now all the isometries. So now we extend, and this is why your example would not work and this would work. If I take all the isometries of ADS, they are the same as the conformal group of the boundary. So they are related to the conformal group of the boundary. They are mapped there one-to-one to the conformal transformations of the boundary. For each conformal transformation in the boundary, what this means is for each conformal transformation in the boundary, I can find an associate transformation that leaves the metric of ADS invariant. Okay? So there are, for each transformation, for each conformal transformation, okay? So here there are all these conformal transformations, K mu, P mu, dilatations and rotations. And for each of them, there is an associated isometry that leaves the ADS metric invariant. Okay? So if we were to guess what background, if I were to draw a picture and say that I want to have some kind of holographic duality, and I want to think that here is the boundary of my space-time. I'll already call it ADS, but a priori I would not know. And I want to ask what could be the nature of the fifth dimension, and then I ask what should be this fifth dimension from an holographic point of view, because I know that I want some fifth dimension because of all this holography stuff. Definitely the most natural way, if I want to have a theory which is a CFT in the boundary, the natural completion is to insert it in a background which realizes these conformal transformations as isometries. So I would naturally in this way argue, or I wouldn't say derive, but argue for this direction Z, and that would give rise to this space being ADS. Okay? In fact, the fact that you have isometries of ADS, okay, so the ADS isometries imply the following, and this is a very important implication. Yes?
Do we get conformal anomalies in M+4 superyoungness?
Conformal anomaly is a very broad term. I mean, conformal anomaly, some observables actually do not transform as we expect, but that get some extra terms because of anomalies.
Yeah.
For some, yes. For some, no. It depends on the observable.
Okay. But that doesn't modify this picture. We can still do the story with ADS.
That's a good question. Then you would have to say, oh, if there is an anomaly in EM-Mills, is there also an anomaly in this in string theory? It better be. Otherwise, they could not be equal. And indeed, people, in the examples where people found some kind of conformal anomaly, an example is the following. So you know that under a conformal transformation, you can map a circle to a line, to an infinite line. Okay? Is it familiar to everyone? So you can take a circle and map it to an infinite line. Okay. Good. So And now you can consider a trajectory of a quark that goes around the circle and study its interaction with the gauge field, and you get some finite result. You just draw a circle, a quark going around the circle and exchanging many gluons. And the picture that you would have in string theory, once you exchange many, many gluons, is like a dome. You see? You have a string that occupies the interior of this circle. And this is indeed some non-trivial result. So mathematically, this is computed by what's called a circular Wilson loop. And you compute this interaction of the quark going around the circle with the gauge field, and you get some finite result. And you compute the same thing for the infinite line, and you get 1. And they don't agree. And the explanation is an anomaly. And then it's also explained in the string theory language that indeed there is a particularity if the string goes to infinity or not. You lose a little bit of area. And whenever there is some subtlety like that, you better have an explanation on both sides, and things better agree. Okay?
So how do we fix those anomalies? And because for the Wilson loop and the minimal surface area in the string theory, they don't agree at loop level in some cases. But then how do we fix that disagreement?
I don't know. What are you referring to?
So yeah, because like before we calculated that you have Wilson loop in A equals 4 square million, and using localization, you calculate the loop fraction, and then you have the effective action, like PBI action for difference in string theory, and you calculate loop fraction, and you find that they don't agree. So is that because of the anomaly you said, or it's so?
I'm not sure. I'm not sure. You should tell me more about this computation. I don't know this what computation you refer to.
So my point is, if we do have those kind of conformal anomaly, and like how do we find the correspondence in string theory?
Well, okay, first of all, whenever we have an anomaly, we should not. I mean, anomaly looks like a bad name, like Frankenstein or something. But an anomaly often has some physics to it. Each anomaly is related to a particular quantity. We should understand what's the physics of it, why do we have it, and is it really a problem? Is it a mathematical thing? Is it a physical thing? So we should be a bit explicit about what we are describing. So in this case, for example, it's related to the fact that the Wilson loop has to be regularized, and when we study these particles, if they go all the way to infinity or if they stay at finite length, we have to think about the radiation of the gluons and things. If they radiate from infinity, they might not arrive here. I mean, we should analyze case by case. I mean, I don't have a general answer for anomalies in physics in general. I don't know the answer to that. And I also don't know in particular the paper that you refer to, so you should tell me more about it if you want.
Okay.
Okay. Very good. So, but what I wanted to say is the following. ADS isometries have a very important implication. They don't prove ADS, but they make some aspects of it less remarkable and less, they make some aspects of it, at least they explain some aspects of it. They imply the following. Suppose I take the boundary of ADS, okay? So this is Z equals 0. Which I remind you before was R equal infinity. And I consider a correlation function of a bunch of operators, like 3, for example. And I consider it's in some quantum process, where by this I mean a propagator, and by this I mean a vertex, and I integrate over the vertex. And this line can be some massive particle. Okay, not massless. So I take some massive particle in ADS and I study its interaction. So I do quantum field theory in curved backgrounds. And I say that now my space-time has a boundary, and the observables I will consider are, I put points at the boundary of anti de Sitter, throw them inside, study its propagation, integrate over the position of this vertex, and so on, and I get some result. Okay? Now you ask, the fact that I have these isometries, the fact that I have these transformations of the metric that leave the metric invariant, means that I can act on these points and transform them around and explore the consequences of these isometries. Right? And the consequences are that if you define in this way, this is a definition of a correlation function, in this case a correlation function of 3 points, where these points are now points in the boundary of ADS, which is to say the same as flat space. Okay? But I thought of this, I want to think of this as a limit, as the points, I make the points approach the boundary. I took a 3-point function, I made the points approach the boundary, and I studied its 3-point function. And the claim is that this Gn transform like a correlation function in a conformal theory. So I don't have any theory at the boundary, but I define the boundary theory by saying I compute stuff in the middle, in the bulk, inside ADS, and study the limit as the points approach the boundary. Okay? It's definition. Now I don't have a duality. I just have one definition. I start with the bulk, any theory in ADS. Put any theory in ADS. Your favorite theory, put it in ADS, and consider the limit as the points approach the boundary. The fact that you have an isometry in ADS, it implies that in the limit, when the points approach the boundary, your correlation function transforms like the correlation function of a conformal theory in 4 dimensions. And you start in 5 dimensions in ADS, take the points to the boundary, and they transform, they have the same transformation properties, they have the same behavior, as a correlation function of a conformal theory in 4 dimensions. Okay? So I did not prove it. I hope it's kind of simple to do. It's just you carefully think what are the implications of isometries, given that each isometry corresponds to a transformation at the boundary. But it would take me like 10 minutes. I don't want to. But is it plausible? Does it sound reasonable? Okay. But then, okay, all right. So, well, then ADS5 times S5 strings define some conformal theory in the boundary of ADS. So suppose I start with ADS and I say, I'll take my correlation functions, my scatterings of strings, make them approach the boundary, and it will define some conformal field theory at the boundary of ADS in this way. Right? Which one? Right? And now which one you say? Well, it has, it's a CFT. You can show that it has n equals 4 supersymmetry. And this is a consequence of the supersymmetry of the string. If you have some symmetry in the string, some amount of supersymmetry, and you translate it to the boundary, it will imply some amount of supersymmetry in the boundary. Right? This is nature. So you see how much this is inherited by the supersymmetry of the superstring. But you know more. You know that this ADS5 also has this sphere. It also has this sphere, right? And this sphere is what? Is an object that is invariant under SO6 symmetry, right? A sphere is invariant under SO6, okay? It has an SO6 global symmetry. And now you ask, how many theories are there which have n equals 4 supersymmetry and SO6 global symmetry and are 4-dimensional conformal theories? There's only one. So in this way we prove ADS-FT. Okay? Okay, so it is n equals 4 super Young Mills. Okay? So this is what people say, that there is this argument 5 which are symmetries. And what was the caveat? Why wasn't this, why were we joking? Why isn't this a serious proof? Well, for various reasons, one of which is that string theory is not really well defined. Is that really, for example, in practice in ADS5, we don't know how to construct the vertex operators of the string. When I told you that what is string theory? It's a correlation function of vertex operators. What are the properties of these vertex operators? They should have this dimension 1, 1, remember, so that we can integrate them over a worldsheet and so on. Constructing vertex operators in a conformal field theory, it's easy if your conformal field theory is easy. If it's a conformal field theory of free bosons, well, then it's trivial. Just e to the ikx times some dx's and so on. And you start constructing vertex operators at breakfast, and it's easy. A conformal field theory corresponding to the string theory in ADS5 is a more complicated conformal field theory, and people did not define it yet properly, defining all vertex operators, studying it in detail. So it's definitely not a super mathematically well-defined object yet. People don't, there are many things in superstring theory in ADS5 that people don't know how to clean up and how to define in detail. If this side was very well defined, I think yes, this would be kind of a derivation. On the other hand, n equals 4 superior mules, yes, it's totally well defined, it's a quantum field theory, a conformal field theory, and so on. But the argument doesn't go in the other direction, it just goes from the bulk to the boundary. But again, like all other arguments, I think it's once providing more and more and more evidence, we are, I hope, becoming more and more convinced that it must be true, but it is not bulletproof. Okay? In particular, there is a very nice exercise that you can do to make this more concrete. So a nice exercise that we could imagine doing is the following. Consider heavy particles. Heavy particles is a particular limit of massive particles. It's massive, which are heavy. So if they are very heavy, how does this picture here simplify? What happens when particles are very heavy? What happens to quantum mechanics when you take a particle that is very heavy? Sorry? Sorry? Just becomes classical, right? A tennis ball, we don't need quantum mechanics. The particle just becomes classical. So a particular example, if what I'm saying is true, is the following. I can imagine considering this curved spacetime, ADS, right? And study this classical toy model where I consider, for example, a bunch of geodesics. Right? I just consider geodesics moving in this space-time. That's the classical trajectory of the string. And what do I do with the geodesics? I say that this correlation function is proportional to e to the minus the mass times the length of the geodesics. Right? That's the weight I get. And the length of the geodesics depends on this point. So what fixes this point? This P is the optimal point. It's whatever point gives me the minimal length of the geodesics. You see? So now it's a totally geometrical and fun problem to do. Find the point which is optimal, compute the length of the geodesics, and so on, and see that what you get should be what you should expect from a conformal field theory. x1 minus x2 to some power, x2 minus x3 to some power, and so on. Okay? So this will be this week's homework. Okay, so, but if the homework is clear already what you should do, you can already start doing it. But I think we will prepare a more guided homework to help you step by step do this exercise. Yes?
What would happen if the particle is too massive?
If it's what?
Too massive?
Too massive to form a black hole and stuff like this? Well, then it forms a black hole and stuff like this. No, here I want some particle to be very massive, but just some without gravity. Just quantum field theory, forget about gravity. Some limit where I don't care about gravity, I just have some heavy particle. You have various scales, right? You can have a particle which is much heavier, but still much lighter as not to form a black hole. So
like these extremely, like cosmologically heavy particles would not...
No, not so big.
And like the CFT.
Oh, they do have, but that's a different. They do have. Yeah. I can explain, but this is that would really be a detour. So there are two different kind of particles you can put. So big that they deform the space-time, or they don't. Right? And that's related to how big they scale with n. If as scaling with n, they don't scale. If they are order 1 with n, they are probes. If they scale with some powers of n, like some operators that really want to emit many, many, many closed strings, then they will have the power of back-reacting the geometry. So there really is a distinction between operators of various scalings with n that tell us whether they are planets or tennis balls or electrons and so on. Okay, so this is one more comment. Maybe for completeness, and now that we say that there's only one theory, let's write what n equals 4 super Young Mills, what's the action of n equals 4 super Young Mills, just for completeness, even though we will probably not use it much. Okay? So what would be the action of n equals 4 super Young Mills? Well, as we said, the trick is the following. It's the reduction to 4 dimensions of the action of n equals 1 super Young Mills in 10 dimensions, which is just f m n f m n, so trace plus psi d psi. Okay? So that's a theory with, let me make sure I'll put everything correct. Oh my god, it's a mess. Okay? So we take this theory where these indices m and n, for example, run from 0 to 9. So these are the indices. I start in 10 dimensions. And then I say that I start with this action, but then I postulate that the fields only depend on 4 dimensions. The other dimensions, nothing depends on them. Like I compactify on those directions. Okay, give me just 1 second. Let me see what. Okay. So just to be explicit, for example, when we write trace of psi d slash psi, what we mean is what? What do we mean by this? Let's try to put the indices on this. So let's see. So we have psi A with indices A, B. Okay, let me first write it and then we'll put the indices together. We have gamma matrices that contract this slash. Then we have covariant derivative, which means d psi plus commutator of the gauge field with psi. Okay? So now let's make sure we understand all the indices in this business. So first of all, there is a trace, right? There is this trace because things are matrices. They are n by n matrices. So this psi is an n by n matrix, so there is some index AB. And this psi is also a matrix, and so are this product of 2 matrices here. So here there is an index BA. So this multiplies the 2 matrices and takes the trace. Then psi is a fermion in 10 dimensions, so it has an index A, and A runs from 1 to 16, whereas these ones run from 1 to n. Okay? Then we have derivatives that have an index m, where m is a space-time index that runs therefore from 0 to 9. And this index m is contracted with the gamma function, of course. The gamma function that has indices of the fermions, A, B, and the fermion contracts with some index B. Okay, and here A has some index M, psi some index B, and we sum over these indices. Okay, so just to be very explicit, such that it's clear what we are doing. Okay. Yeah, good. Now, when we do it, when we do this reduction, then this becomes the following. So you see that fmn becomes, I'll write it and then you'll see if it's clear or not. Fmn becomes, if the index are mu nu, right? So we will divide the index m into 0 up to 3, this is mu, and 1 up to 6, and this is m. You understand what I'm doing? Okay, it should be 4 until 9, and then I shift it.
Why does A go from 1 to 16?
That's just the size of these fermions. It's just how many components the fermion have. In the same way that in 4 dimensions fermions have 4 components. It depends on the dimension. It's 2 to the d over 2, something like that. Okay? Okay. So we start reducing, and f mu nu becomes f mu nu. But then you can have the following. You say that you decompose your a mu, and you say that your am, and you say the first components become a mu, and the last ones become phi m, where these are the last components of a mu. Okay? And then what happens? When we have an index mu and an index m, you see that what we get is just d mu phi m, d mu phi m, where d mu is covariant derivative. And you see there's only the term with derivative with respect to mu acting on phi m. There is no term with derivative with respect to m acting on a mu because we reduced. So we said nothing depends on m. So there's no derivative with respect to m. Okay? And then, if both indices are m and n, what do we get? If we take both indices of ff to be in this range,
kinetic the term corresponding with this delta scale.
What we would get is, when we write this, what we would get is just a commutator of the scalars, phi m, phi n, which is what appears in a covariant derivative, right? Square. By square, I mean you multiply both and contract the indices, right? So in each covariant derivative, there is the commutator and the derivative. But here, you only have the commutator because nothing depends on m or n. Okay? Similarly, the fermions, you get two different types of terms. You get psi plus, now we get the fermions, psi, gamma mu, d mu psi plus commutator of a mu with psi. This is if the index m is a mu, plus if the index m, if the index capital M is small m, there is no derivative, and we would write plus psi gamma m commutator of phi m with psi, where I'm omitting the spinor index because it's obvious where to put it. Okay? And this action is the Lagrangian of n equals phi, which I never remember. The only way I can remember is if I do the reduction from 10 dimensions. In 10 dimensions, you see it's very simple. Just f squared plus psi d psi. And when you reduce, you get a bunch of extra terms, some interaction and some cubic interactions and so on that are very naturally inherited from 10 dimensions. But the point is that this action, which is a 4-dimensional action, you see, if someone gives you this action, you can say, it smells 10-dimensional. Right? There are many features here that look like they come from 10 dimensions. The gamma matrices that appear here you have some of them contracted with mu and some appearing in the interaction terms, and together they form the gamma matrices which provide a representation in 10 dimensions. Right? So you have these gamma matrices that obey gamma m, gamma n plus gamma n, gamma m equal eta mn in 10 dimensions. And this is the gamma matrices that you see here. You see this commutator of 6 scalars. And you say 4 plus 6 is 10. It looks like there were some extra gluons that I got rid of. And they do, of course. But it's not a coincidence. If someone shows you a commutator, you should always think, oh, probably this came from a reduction. Because typically that's what happens. There was some gauge field, some covariant derivative, and things reduced, and you got some commutators in lower dimensions. So even though it's a 4-dimensional action, it's an action that, of course, remembers that it came from 10 dimensions. And indeed, you see that in this action, we have various degrees of freedom. We have the A mu's, and we have the phi m's in particular. And you see that before they were the same thing. Both were gluons. Right? Both were the degrees of freedom of the open string. But now we separated into 2 groups. Which, roughly speaking, we can now interpret and can now say that, well, in the brane picture, it's very natural. Because when I put open strings here, there are 2 different kinds of polarizations. Either they are longitudinal to the brane, either the index mu is longitudinal to the brane, or they are perpendicular to the brane. And the phi's are nothing but the degrees of freedom perpendicular to the brane. They correspond to like local fluctuations of the brane in the directions perpendicular to it. Whereas the gluons are the excitations longitudinal to the brane. Okay? And where is this SO6 symmetry? The SO6 symmetry is exactly the symmetry that rotates these 6 scalars. You see, you have 6 scalars here, and there is this symmetry that rotates these 6 scalars. Which is, of course, natural, because we had these D3 branes here, and we had these 6 orthogonal directions, and there was some rotation symmetry in this orthogonal space. So everything matches concerning symmetries as it should, and as I said above. There was a question, yes. Maybe here first. There was this question first, yes.
Yeah, so just a small question about 10-dimensional algebra. So the gamma matrix is 32 by 32 in 10 dimensions. But you said
but you can write them in. You can always write them in blocks, diagonal, 0, gamma, gamma, 0. And the gammas that I wrote there are the ones that appear in the block, the 16 by 16 blocks.
Well, that's right.
Yeah. Other question?
Where's the supersymmetry?
The supersymmetry here you don't see explicitly. So here, the n equals 1 supersymmetry is a symmetry that transforms an AM into a psi. Okay? So here there is a symmetry that transforms a delta A into a psi. And okay, we can try to do it. Let's see if I can do it. If I put an index m, for this to make sense, I need some gamma matrix with an index m. This guy has an index b. To get rid of this index, I put an a, b. I still have an a. I contract with a spinner epsilon a. So this is the supersymmetry transformation with a small parameter, fermionic parameter epsilon a, transforms a gluon into a fermion. This is the only thing I can write. And similarly, there is another transformation that transforms the fermion into a gluon. So this is the n equals 1 supersymmetry. If you reduce this transformation to 4 dimensions, they give you now various transformations that transform gluons into fermions, but also scalars into fermions. And they give a more complicated group, and that's n equals 4 supersymmetry.
And the n is the number of generators?
N equals 4 is related to the number of generators, yes. Yes. This dot 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 stand that there is also another transformation for the other field. Okay, so this is the n equals 1 supersymmetry, and there is analogously an n equals 4 supersymmetry transformations. Okay.
I not properly understand the reduction to 4D. So when you reduce the Hermes series to 4D, like you just split the AM into the scalar part, I mean X phi m and the AMU part, substitute that and write down the program.
The key thing is that derivatives, I dropped derivatives with respect to these directions. I said dm equal to 0. I say that my fields only depend on x0, x1, x2, and x3.
So you just drop it?
Yeah, I just set these derivatives to 0.
And then we are losing the gauge structure in the...
Then we lose, yeah, exactly. Then we lose this gauge structure in this direction. So what were before gauge, these fields that transformed before now are scalars. Right? So now this becomes 6 scalars. So it becomes a 4D gauge field and 6 scalars. And these 6 scalars, they transform under the vector representation of SO6, and this is this SO6 global symmetry. Okay. So this is symmetries. And now I would like to add an extra point, to make a further comment here, which is related to some theory by Weinberg and Witten. So let me write the theorem exactly how they write it, and let's prove this theorem. Because this theorem is another paradox that looks very threatening to us. So let's write it, prove it, and then find how we can escape. Where do I have it? Any question while I look for the paper? Okay. So the theorem states a theory with a Lorentz covariant with a Lorentz covariant energy momentum tensor T mu nu, for which the integral, if I integrate T0 nu, right, over d3x, so I integrate over some space at some fixed time t, I integrate over space the 0 component of the stress tensor, and in this way I define my form momentum p mu. Okay, so this is the form momentum. So a theory with a Lorentz invariant tensor for which the form momentum is given by this, they claim that such theory, a theory for which cannot contain massless particles of spin greater than 1. Okay.
Can you elaborate a little more about for which part? Like, so.
I will prove this. So I think while proving it will become very clear. But tell me what, sorry?
I don't understand. Like, for which P mu is what? Like, P mu is.
Okay, so a theory with a Lorentz covariant energy momentum tensor, and then if it has, and then its form momentum is this.
Oh, okay.
Cannot contain massless particles of spin j bigger than 1. Okay? Okay, so good. So let's prove it, but before proving it, let's be worried, because what we are about to say is the following. We said that n equals 4 super Yang-Mills, here is a Lagrangian. I can construct a stress tensor, right? I just construct a stress tensor for this theory. I can construct a test tensor for any gauge theory. I take a gauge theory, I construct a test tensor. And then I say that gauge theories secretly describe gravitons. But gravitons have spin bigger than 1. Okay? So if I can prove this, am I disproving ADS-CFT or what? We will see what's the caveat and how exactly it is not a problem. Okay, so for that, let's consider the correlation function of a single particle, single massless particle with momentum p in sandwiched with t mu nu and p. Okay, so consider a single particle of spin j and consider this 2-point function. Now in the limit of p prime goes to p, what happens to this correlation function? Well, if I want to write it, the only thing I can write with these indices is it will become something proportional to p mu, p nu, okay? And then I'll do the following. I'll put f over 2 pi cube times the energy okay? This is my normalization. What I want to put, that Lorentz invariant tells us this is the only thing you would write. And then, if you see now that if you put nu equal to 0, when you put nu equal to 0, you get exactly the energy, which drops out. And if you want this component 0 here to describe the energy of your state, in that case, you want f to be equal to 1. Okay? So it's just normalization to make sure the normalization works out on both sides. Yes?
Why can't you have a eta mu nu term? P square eta mu nu.
Why can't I have p square eta mu nu? Because p square is 0 because the particles are massless. Okay? Single part, and this is massless. So with these dimensions, I can only write this.
If you put the energy in the denominator, like isn't that the whole term is not Lorentz invariant?
Yeah, that's true. But these particles, they also transform under Lorentz, but that's true. Yeah. I don't, yeah.
The expression over there, you're trying to write down everything Lorentz invariant.
So let's see what happens here. So let me address your question. So let me write an equation and it will become clear. So the energy times delta function of p minus p prime is equal, tell me if you agree, with p times the operator that measures the energy, which is d3x t0 0 p prime. Right? This is just the operator that measures the energy, which is equal, this is at some point x, but by translation I can say that this is equal to integral d3x. I can translate this operator to the origin and write e to the I x p minus p prime, right, times the expectation value of p t0 0 p prime, and therefore this sets me at a delta function of p minus p prime, right, times some 2 pi cubed, and therefore I get that what I expect for p t0 0 p prime is to become the energy divided by 2 pi cubed. And this is indeed what's consistent with this normalization. Okay? Okay. Then my point is that this expression is non-zero. Okay? this expression is non-zero. So our goal is to prove that it is zero and therefore reach a contradiction. Okay? This is how we'll prove the theorem. Okay? So on the one hand we expect this non-zero result, some nice non-zero result. If now I show that for spin 2 it is zero, then I have a contradiction and therefore spin 2 cannot exist. Okay? So the goal is instead find equal to 0 instead of not equal to 0 for spin bigger than 1. Okay? Okay. So the idea is now to first go to the center of mass and consider this to be P and this to be P prime. Consider first a configuration where P is equal to the energy and P prime is equal to the energy and minus P. So now we consider two different massless particles, okay? And I go to this configuration here. Okay? I can always do it, because if they are two different massless particles, and then P minus P prime is time-like, P plus P prime is time-like, right? Because if I throw two light rays one after the other, I get some timeline distance, so I can always go to the frame where this timeline vector has no space component, and this is what this is. Okay? So we go to this center of mass, and this is the axis P, so this is the axis P, and now we'll consider rotations by an angle theta around this axis. So if I do a rotation of an angle theta around this axis, what happens is that particles of spin j acquire a phase. That's how we measure the spin, the helicity of the particles. Now particles have some helicity plus minus j. Okay? And under this transformation, this particle goes to e to the plus minus I theta j times the same particle. While if I do the same thing for P prime, I go to e to the minus plus, the opposite sign because P prime is coming in the opposite space direction, e to the minus plus I theta j times P prime plus minus j. Do you agree?
Sorry, what's theta?
Theta is the angle by which I rotate. I rotate with some angle theta in this axis. Okay? Along this axis. So there is the axis of collision, and I rotate along an angle theta in that axis. Okay? And therefore, we have that my matrix element P, T mu nu, P prime, okay, goes to e to the plus minus 2I theta j. So that's how it transforms. Right? If I apply a rotation to my vectors. Okay? On the other hand, I know that this should be the same as rotating the indices. In other words, if I rotate everything, I do nothing, right? I rotate everything, I do nothing. Which I can write as an equation that's saying this is on the other hand equal to P T mu nu P prime, and then, okay, no, sorry, rho delta, and then I rotate my index rho for some angle theta, and I rotate my index delta for some angle theta. Okay? I'm just saying that if I do everything, I do nothing. So I can either rotate the indices or rotate the particle. Okay? Is it clear? But now, what are these rotation matrices? These rotation matrices are some matrices. What do they have inside the matrices? This rotation matrix of vectors. They have ones, they have e to the I thetas, and they have e to the minus I thetas. Like a bunch of cosines and sines. Yes?
Could you please write in the upper bowl?
Yeah. Right? So these rotation matrices contain 1, cosines, and sines. Right? You agree? So if you make any linear combination, if you act twice with this matrix, on the right-hand side, here, on the right-hand side, I can have e to the 2I theta, e to the I theta, and so on, all the way to e to the minus 2I theta. Just because it's what this is made of. I can only go at most e to the 2I theta if I take an e to the I theta from this matrix and another from this matrix when I multiply. Right? So if j on the left-hand side is bigger than 1, like if j is 2, I can never get e to the 4I theta. That's just impossible. If j is 3/2, I can never get e to the 3I theta. You agree? And therefore, this implies that if j equal to 1, then the matrix element is equal to 0. That's the only way I can satisfy this equation. Okay? And if the matrix element is equal to 0, but it shouldn't be 0, it means this particle is not there. Okay? So this is a beautiful theorem by Weinberg and Witten, where they use, because, I mean, some people sometimes say that maybe gravity is emergent and I can have some gluons and blah, blah. And they said, okay, let's try to see if this is possible at all in nature. So they said, let's suppose that GR is something emergent from some gauge theory and so on. Could it be true? And they say, no, it's not. Look, you cannot have gravitons being emergent from a theory with a stress tensor and so on. Okay. So now, a few comments here. Comment 1 is, but we have gravitons. We observe, we have LIGO, detect gravitational waves. Okay, so there are two obvious comments. Comment number 1, in GR, T mu nu equal to 0. So no contradiction. Right? In GR, the total stress tensor is 0. That's how we compute variation of the action with respect to the metric equal to 0. So total stress tensor of GR is 0. So no contradiction there. Okay? So if you have a theory of quantum gravity, the stress tensor is 0, and then you are good. Now, in n equals 4 super Young-Mills, however, in a gauge theory, stress tensor is not 0. Stress tensor is the stress tensor. So in Young-Mills, on the other hand, the stress tensor is not 0. So naively, you would say that we were drawing these cartoons and saying, oh, there is these cartoons, and sometimes it looks like a tube. That tube is probably a graviton because it's a closed string, and so on. And you could say, no, it cannot be. It cannot be because of this theorem. So what could be the solution to this paradox? What could be the loophole that Weinberg and Witten did not think about? Sorry?
Because n equals 4 super Young-Mills is not really indicated. So
No, I don't think, I did not use that it's abelian or not. No.
Is the mass?
Sorry?
Is the massless particles?
The particle is massless, yeah, the graviton would be massless. The graviton that, in EDS 5 times S5, there are massless gravitons, yeah. So it's massless.
Is it obvious that the stress tensor integrates to the momentum operator?
I think so, yeah, that's the definition of the momentum operator, yeah. Just measure the energy, that's okay. The caveat is that, but the graviton is not in 4 dimensions. the graviton is emergent, but it moves in one extra dimension. And this we were not prepared to in this theorem. This theorem tells us nothing about that. About whether, in a theory in 4 dimensions, we could have some emergent graviton degree of freedom that behaves like a massless particle in one more dimension. Okay, that we said nothing about. We just said that if you have a 4-dimensional theory, you cannot have emergent massless 4-dimensional gravitons. We did not show that we could not have emergent massless 5-dimensional gravitons. Okay, so it's the same solution to the paradox of the flux tube that went into the higher dimensions, and that's why it was possible to think of it as a string, even though it didn't look like a string in 4 dimensions, and this is also the outcome of this small puzzle. So I will add to the list of things, and today we will also end up a little bit earlier. I'm almost done. So I will add to this list 6, this Weinberg-Witten argument from the 80s. Again, indicating hints that if such duality ought to exist, it better not be in the same dimensionality. So it's again related, if you want, to holography and to many other things. Okay. So finally, I would like just to say a few comments about anti-de Sitter 5, which are related to this afternoon's tutorial, which and such that we can, which are related to this afternoon's tutorial. Okay. So, any question otherwise? Yes?
Where does this derivation assume that we are in 4 dimensions?
No, it doesn't assume that we are it works in any number of dimensions, but it assumes that the particles that you are studying are in the same dimensions as the dimensions of the indices of your stress tensor, right? So you have some stress tensor with indices from 0 to 3. Then you say, let me show if gravitons in 4D can exist. Right? If you have some stress tensor with indices from 0 to 5, you'll see, can I have gravitons in 6 dimensions? But what we have is wilder. We say, I have a stress tensor with indices from 0 to 3, and then I have gravitons moving in one more dimension. That was not there. That it's different. It's emergent. And that we cannot say anything about. Okay. But I think it's an important thing. It tells us that whenever you will have ADS-CFT dualities, we could ask, is this holography something solid? Does it need to be general? Can there be some theories where the dual and the theory have the same dimension, for example? Could I have some gauge theory where the dual string theory is also in the same number of dimensions? Well, if so, you would have to fight a little bit harder with this Weinberg-Witten theorem, right? Right now, we have a way of avoiding it. I don't know. Imagine the duality was between n equals 4 super-Young mules and ADS4 times something superstring. And then if someone shows me this Weinberg-Witten, I would not know how to get away. Okay? So it's again the construction always escapes whenever someone tries to disprove ADS-CFT. It's typically not a good idea, but yeah, it's amusing how it works. Okay, so I'd like to make some comment because this is something that people often get confused about ADS5 and this picture that we have a quantum field theory at the boundary of ADS5 and so on. So the metric of ADS5, right, is the one we derived it was, help me out, I forgot, it's something like R square over L square dx mu plus L square over R square. Yeah. dr square. Right? So this was the metric we derived in ADS5, and this becomes equal once you do R goes to L square over Z, became L squared times this nice metric that we like a lot, dx mu plus this z squared over z squared. Okay? Now, the boundary of ADS5 is z equal to 0 or r equal to infinity. That's where this space-time ends. This coordinate z runs from 0 to infinity, and the boundary is z equal to 0 or r equal to infinity. Which makes total sense. Remember, ADS5 is the region close to small radius, right? So in the full metric, before we took this limit of zooming in close to the horizon, there was r, and r equal infinity was flat space, and r equal 0 was going close to the branes. So now if you are close to the branes, r big is when you are going further away from the branes. Okay? So r big is leaving ADS. It's indeed the boundary of ADS. Okay? And when we consider this r equal infinity or z equal to 0, this is the boundary. And it's at the boundary that we put sources like this 3-point function of points at the boundary there. You see, I put 3 points at the boundary, and I see what's the net effect of putting some sources at the boundary. So it's at the boundary of ADS that we put our sources. Okay? So this is where we put the sources. So people sometimes say that there is a duality, and you remember in this holographic sense, I say that I have some space-time, and at the boundary leaves some holographic theory. So people will say that n equals 4 over Young-Mills. Often people like to say it's at the boundary. And okay, this is ontological once more, so I don't care. People can say. So it's at the boundary. But let's say it and see what it means. So let's say n equals 4 super Young-Mills, because it's at the boundary of this ADS. It's where we put the sources, and so on. It looks reasonable. But notice that r equal infinity or z equals 0 is not where we put the branes. The branes, it's the opposite. It's r equal to 0 or z equal infinity. This was where the branes were originally. So then people get confused. So, well, why are we putting sources at the boundary if the branes were at z, well, at r equal to 0? Okay? So why? But that makes total sense. There's no contradiction at all. It's just some confusion. Maybe I shouldn't even try to confuse you to clarify you. I should just be quiet. But because this background, if I want to put a source, I'm not going to put the source in the middle of the background. I'm going to put the source when I'm entering. I say, okay, here you are, go play, and then the string goes, and then I receive the string at infinity again. I'm not going to start putting sources here. Similarly here in the brain, if I want to say where does the brain start, well, I throw things from far away, let them interact, and receive them again. I don't want to start doing probes in the middle of my experiment. So if we were to choose where is the region where I interact with the brains, I say I interact far away. I start far away, not to mess up things. I throw things, let them interact, and receive them. So in both cases, if I want really to have some asymptotic region, then some interaction, and then some asymptotic again, it is what makes sense. It's indeed to prepare probes at infinity, to send them at infinity, and receive them. Okay? In other words, it doesn't, but the more correct thing to say, but again, more correct or less correct, as I said, it's up to you. But the way I would rather say is the following. So here there is a background. Where is the brain? There's no brain. Because as we said, we either use brains or we use background. The background, the full thing, everything, it's everywhere. The brain is not there precisely because we have the background. Because we removed the brain and said instead of the brain we can have a background. And it does the same job. It's an effective description of the brain. So I don't like saying, where is the brain in ADS5? Is it at r equals 0, at r equals infinity? No, it's not there. It disappeared. That's why we have ADS5 after all. Don't put brains twice. You either have ADS5 or you have flat space with brains. Don't overdo it. That's too many brains. And in flat space, we have the brains, if you want, at r equal to 0, but we prepare things far away from the brain. So this picture here, this is called this metric, it's called Poincare metric. It's the Poincare coordinates. And it is the metric that is the most convenient one from the point of view of deriving this decoupling argument. And it's also very friendly to this renormalization picture where we say that things that happen very close to the brain are UV physics, things that happen far away from the brain are infrared physics, because they describe correlation functions of nearby points or faraway points. So this has this very nice geometrical RG interpretation, this connection to the conformal group and this dilatation stuff. And it's the metric that comes about most naturally from the point of view of the derivation of the decoupling argument. But there are other incarnations of ADS, other ways of seeing ADS that you will explore in the tutorial. You can actually think of ADS as some sort of sphere in some different coordinates, or some hyperboloid, some pseudosphere. And you can also think of ADS, if you think it properly, as really a box. I was using these words, I have a gravitational box, and I can think of ADS also as the interior of some cylinder. And that interior of some cylinder picture is, it's personally my favorite, and it also makes some other things very powerful and manifest, and I will leave some stuff to fill in next time, but I just want the following to be plausible. So the idea is the following. Next time we'll do the following. So we will analyze the geometry of ADS. This is not done because I don't have time now, but I'll do it on Monday. So we will analyze this geometry of ADS. We will find, and you will find in today's tutorial, that one of the incarnations of ADS5 is as a cylinder. It's one of the ways of describing ADS5. It's also a cylinder. And this is ADS. And this thing here is the boundary of the cylinder, so it's the boundary of ADS, which in these variables, it's not flat space, but instead it's time evolving times a sphere. Okay? This gives you a duality between putting n equals 4 in a sphere times time and putting string theory in a cylinder. So it's a different incarnation. It gives you a different version of the duality, which is just related by analytic continuations. It's almost the same. It's almost the same. But it will give you a duality between putting the conformal field theory on a sphere and putting the string theory on a cylinder. Okay, it's a slight modification of the standard one that we derived. But this will allow us to derive the following. I just want to anticipate it already. That one of the symmetries of this background is time translations with respect to some time. And that time is the same inside the cylinder and outside the cylinder. But once you have a variable that is associated to some symmetry, there is some physics in it. Then you know that as conjugate to this variable, there are energies. So now, by going through this geometry, we will then be able to say that take the energies of any state that you can get in n equals 4 super Yang-Mills on a sphere. You'll see that when you put a quantum field theory on a sphere, which is a compact space, you get a discrete spectrum, like the hydrogen atom. So you get some spectrum. On the other hand, the same time t is also the time t that controls the evolution inside ADS. So this should be equal to the spectrum of strings in the cylinder, which is global ADS, which is called global ADS. Okay? So I did not prove it, I just made it slightly plausible that such thing could exist. But this will be our example of a first entry of this dictionary that tells me that if you are powerful enough, imagine you are very good at string theory, then you compute all energies of all quantum states of string theory, and someone else is very good in CFT, and he computes the energy of all states in the sphere. You get two spectrums, and then you do like in CSI, you put one on top of each other to see if the suspect is correct, and you should see that the lines match perfectly. Okay? So this is just one example of many of this dictionary that we should have, and for any quantity that you should be able to come up in Yang-Mills, I should be able to come up with a twin version in string theory. And this is the simplest example of it. But this will be what we will start by next time. Okay, thank you. Questions?